Preparing, recording. Good. All right, so today is solving equations using logs, but first we have to look at a few key concepts over here. As mentioned, the main log button on your calculator is log base 10, right? Log base 10. So what do you do when you have log base 4, right? How do you get rid of that? Okay. So the base change of base formula allows you to do so. And as mentioned again, it's not as if you cannot do log base 4. It's just that technology and for convenience, we bring it to log base 10. And I'm not sure actually if the proof for change of base, I'm sure it came way before it, but it was a commitment to change everything to base 10, which then they used to have tables they'd have to look at. Now our calculators follow that same suit where technology is on base 10 most of the time. Yes? Yes. So when you have a change of base, let's do one practice problem right here in red. If you had, say, and this is abridged again, there's videos online if you need it, link to Edmodo. Let's say if we have log base 6, log base 6 of 5. Go do the change of base for that. And then you see once you've converted it to the change of base to a base 10, you could use the calculator just to find the actual value. It won't be an exact value, so I don't mind for these if we're leaving it as a fraction of what? Log 5. I mean, it kind of follows. This one is, I mean, spatially, this is a subscript, so that goes on in the denominator. Log base 5, excuse me, log 5 log 6, over log 6. You can do that in a calculator, right? I don't want you to look into logs as this like mystical thing. Logs are just helping us to find the exponent. Find that exponent when we don't know it. Okay. Remember in the beginning we had, I think in here it was like 71. 10 to what power gave us 71? And we went over and over and over. Oh yeah, 1 sec. I have to pause. All right, go for it. Go for it, Serena. Oh man. One more time. Yeah.
One, two.
All right, we did it. Oh, I'm sorry.
1, 2, 1, 2, 3, 4.
Okay.
That was so bad. You know what?
We need to redo that.
No, we don't need to redo it. Really fast. 1, 2, 3. All right, welcome back. For all my fans in Brazil. Yeah. That's all you're missing. All right, let's transition. Transition back. That is what you're missing here at West Campus. It's amazing. Is everyone okay with change of base? I know we paused for a second. But you see how we're going to use that? Okay.
Yeah.
I'm not sure if you... No, you didn't do it yesterday, I know. Okay. Now, if you look at this limit, it's saying 1 plus 1 over x to the x power. If you approach x, as x approaches infinity, so it gets larger and larger and larger and larger, right? This becomes 1 plus a very small number. 1 over, a billion is a very small number. Raised to, it's a really strange situation. If 1 plus a very, very small, it's getting closer and closer to 1, but the exponent is getting closer to infinity. Now, if this here ever reached infinity, then it would just essentially be 1 plus 0, right? Because 1 over infinity would be a very, very small number. So it would be 1. It's basically as the expression here on the inside approaches 1, and as the exponent approaches infinity, what happens? What happens is you end up with the number e. Mm-hmm. The number e, I'm going to try to look it up because one of my college professors brought up how the number e can help you decide which potential romantic connection that you have over your life, which one should be the one that you marry. Because if you're interviewing a secretary, you don't want to hire the secretary, the first one you interview. You don't want to wait too long and hire the very last person that could come in the door. And the letter E is actually used in finding that kind of sweet spot where you haven't seen too little of the options and you haven't gone past and seeing too many. You can see that this is a weird situation, right? And the professor, I'm going to look it up and try to remember the exact details, but it was looking at how that can help you make selections over a bunch of different options. So I thought that was kind of interesting. And I like to bring up, the dating rules of math. So this is like part 2. This is part 2. And if you're for marriage or not, it doesn't matter. It's just talking about finding that perfect match. And it's kind of silly also. It's anecdotal. Exactly.
Thank you.
All right. So when you have a base e, when you have a base of 2.71, ... then you end up with the natural log. Ln, natural log. In Latin it would be logarithm natural, something to that extent. So that's why it's Ln. Okay, it's a log natural. No.
Perfect.
So when we have this, we just want to remember it's a base e. It doesn't change any of the rules that we learned over here. It doesn't change anything, even the change of base formula we can use. But we're going to treat it just like it is another base value. Okay. It just may be written like this. This is more of a notation difference. Okay. So now let's look at what we have for today. Because we're bringing together everything we've been learning in order to solve equations using logs. The key here is to use the inverses to help solve the equations. So this was from the change of base. Get rid of it. But when you have log base a of a raised to an x power, remember those canceled out. Those canceled out. So we end up with just x. Likewise, if you have log base a of x, and that is your exponent to a base a, that also cancels out for x. It's kind of it's spatial. It's if you want to look at the proofs for these, there are going to be some linked videos for that, but for lack of time today, we're not going to prove them. Okay, but this is basically one of the inverses, a way that we can find the inverse. Could you take all those? That was they've been skipped every day almost every time you come. Yeah, I appreciate that. Thank you. So let's look at some examples. These examples go quick. I want to spend most of the time looking at population growth decay. Gene.
Wait, so this is the natural log of EX does not equal natural log of 2.
Right, you're still going off that example from the other time, from yesterday. You saw it on the board.
Yeah.
Okay, what was the exact problem that you saw? We'll look at it.
I don't know.
It was the natural log of.
It was in red, so I thought it was important stuff.
Okay. Let me look at. Let me look real quick because I did take a
picture. Those aren't always true.
Right, you were looking at. Actually, I'm not sure where you were looking from yesterday. Yesterday, Gene saw something on the board that we were. Oh, I see. It was like the flickers. It was like this.
It was near
Is that
that,
the end?
yeah.
Okay. So we had yesterday. We had something like this. Solve for x. Oh, I see. The natural log of x raised to the 4th is equal to 8. Okay. So we had that problem right there. And the basics for this is we know that this is an exponent out top. And we know that when we have an exponent, we can bring it down in front of the log, and it becomes more of a coefficient out here. So we're going to bring that down. And then I want to isolate x, so then I would just divide by 4. The natural log of x is equal to 2. And then once you get to that point, you just have to remember that you can do this. Because the natural log is the log base e, if I decide at this point, these things here, these two equations, these two expressions, are going to become my exponents. I'm going to raise both to the e. Or e is going to be raised to both of these. We've done the same thing to both sides of the equation. So I want you to talk with your neighbor on that. What is that going to cancel out to be? Sure. Aiden, you already knew. Yeah. Yes. So this is going to be a real quick brief because we're gonna see this again once we get to example 3. But in this case, I can create these to be my exponents of the number e. E to the natural log is essentially, it would be this situation where we have log base e of x, right? In that case, we know with base 10 log, we can cancel them out and have it be equal to x. This is just the natural log expressing log base e. So e raised to the log base e, or e raised to the natural log cancels, and we get x is equal to e to the second power, which we can find on a calculator. So the answer wasn't 2. The answer wasn't an identity problem. It was more of an example problem that we had to work out like that. So that's just to start. Let's look at example 1 right here. Now, what can I do, thinking about these inverse log forms here? What can I raise both of these sides of the equation to in order to cancel some things out? What do you think? First, I look to the base. I see it's a base 5. Right? And if you look, if you have a value raised to the log of the same base value, then it cancels out to x. So what I'm going to do is I'm going to say, these are now exponents. I made the two expressions on each side of the equation. I made them into exponents. I said they are the exponent of base 5 now. Okay, you can do that. You have liberty to try things like this. Okay, when I do so, log or 5 of log base 5 of x, this aspect cancels. So you get x is equal to 5 squared, 25. That's how fast these kind of problems are going to go. Because there are only, let's see, we have 4 identities there. We have 2 here. That is pretty much the basis of, that is just the basis of what we are going to use to solve these using the logs. Okay. So let's see. And again, that's the same as if I had 10 log base 10, which I'll write just for you guys, is equal to, log of x. This would cancel to 2 equals x. The proof for that and the wraparound to try to explain this exponentially is a little more difficult than looking at the rules and starting to remember the rules. Okay. So I want you to try this one. What can you raise both sides, or what can you have as a base for both sides in order to get the logs out of the way there? So again, we're going to look at these two things as now reflecting my exponents, and what base do I raise those to in order to really get at this problem? So go ahead and jot it down if you know. If you don't, check with your neighbor right now. Say, hey, what's this?
What's this?
Remember that if you have a base raised to an exponent log base A, if those match, you can cancel those out.
Okay. So you can raise the 10 would cancel out.
All right, let's bring it back. Lincoln, what number should we go with?
10.
10. 10. 10 with an exponent of log base 10. That's why you chose 10.
Yeah.
And if you didn't know, that's why you chose it, or why you were thinking that, anyone in the class? We want to make that connection. If this is log base 2 of the expression 2x plus 3, I would then say those are my exponents for a base 2 out here, so I can cancel them. So watch what's going to happen. This is how we're going to get to actually solving for x. Those cancel. And then I have 2x plus 3 is equal to 5x plus 1. And I'm not going to solve that out because we can do this. We can do these. Isolate x, solve for x. Okay. Let's just do one real quick. How about if I have log base 2 of x is equal to log base 2 of 4. What's your suggestion? Yes. 2. We say that's now the exponent for 2 raised to those powers. We do that because the log base 2 as an exponent of 2 cancels. And here it cancels as well, so x is 4. If you need just another example, I think that's another example you can put in there. We're raising it to or we're saying the expressions are going to become exponents in order to get rid of some of these logs. Okay. Number 3. Here we go. All right. So let's go ahead and think of it this way. If I had 2, let's even make it even easier like this. This is like the day 1 where we started to look at base 10 ideas, base 10, right? So what can I take of both sides here in order to get to my exponent up at 2x? What can I take of both sides? You're going to take the log of something.
10.
Yeah, watch. We're going to go ahead and take log base 10, log base 10, which essentially is just the log, because that's the main one we're using here. Log base 10 of 10 cancels, and we end up with 2x is equal to the log of 5. I should have written that as an exponent. It's right here. You see, that cancels over there. We can take the log of 5. We can then have a decimal that we divide by 2. Or we can just even divide this by 2. Yeah?
So for the example, would we use ln?
Yes.
Okay.
So instead, what I was trying to point out that Jackson sees here is we took a log base 10, right? But up here, we're going to take not log base 10, because we don't have a base 10 in our exponent. We're going to take, well, I'm going to write it actually as if, and then I'm going to have you see, hopefully. If I take log base e of e raised to the 2x, I end up with 2x. That's how I would cancel them out. But we already know, we learned the definition, that log base e is our natural log. Okay, log base e is our natural log. So this is synonymous with the natural log of e, the natural log of 5. 2x is equal to the natural log of 5. And from there, we'd be able to calculate using a calculator or an online simulator here in 5. And we're going to just divide that by 2. That would be our x value. So we still got to be a little clever. We got a new base to deal with, but it's the same rules. Same thing that applies. Same rules. All right. You get the hang of this. You get the hang of this. You got to do a couple practice problems. Probably got to wrestle with a little bit. But have these 4 identities ready. Have what we know now about natural logs. This is going to be helpful. And our 2 really helpful inverse ideas there. All right, who knows about this one? Let's see. A lot of things we could do with this. Anyone have any ideas for this? Yeah, what do you think?
4.
Yeah, see what happens. We raise this to the 4th, or we say these are all exponents. What's going to happen to the left side of the equation? What do I end up with on the left side?
X minus 2.
Yeah. All of a sudden, we've gotten rid of these. X minus 2 is equal to 4 to the 6th, which we could find pretty easily. So what's x equal to? 4 raised to the 6th power plus 2. These are things that we can do. Okay, so it's the other thing you could have seen here potentially is the using the subtraction, but that doesn't really get us anywhere closer. No. So raising it all to the 4th, yeah, that would get us to 1 over that x over 6. Yeah, it's not going to make any difference. So I like the idea of making a new base of 4, working it all the way up. Okay. Let's look at something a little bit trickier. Start with this one. Let's see if we can do example 5. So, with these, the letter E is very important in compound interest. It's important in population growth. And this is the main formula you use. You have two or 3 problems that you have to do in the realm of word problems with population growth. Okay. So growth and decay we've touched on before, but we used a different version. Now we're incorporating the number E. And it's kind of formulaic, obviously, here where you're putting in the starting position, the ending population, the growth rate and time, and all are centered around this base E. Okay, so we're going to set that up. And I want you to look at it yourself for number 5, example 5. Think about how we might set up, where does the 6 hours How large is the population in 6 hours? This doesn't give you units in time, so we're going to go ahead and actually, I'm going to double check that one because I'm not positive on the standard units for it. Oh, got it. Okay. How large is the population in 6 hours? We're going to take time in hours here. So assume that the units for time are hours. Go ahead and plug that in. This is a little bit of calculator work, but this is only the first problem. I'll erase here because we have another set of problems too. This one's more so what you're going to see. Don't look at it. This is a true story. It's just... All right. Okay, what did we do with this? We had, what is the bacteria growth? So the Indian population, 5 e raised to the 2, time will go in 6 hours. So we'll say that this population growth is compounded every hour. So we're saying the units of time are hours. Okay. Now how are we going to approach this problem? What do you think? We're trying to find y. So essentially, if I can reduce this, simplify it, then we'll find our y value pretty quick. So who has the first step for me? All right, is there much of a step? No, not really. Yeah, I mean, you could look at this. You could look here and say, well, I'm going to go ahead and what am I going to do with these two numbers? Have you been saying multiply the whole time? All right, go ahead and get acquainted with that E button on your calculator. 5e raised to the 12 is... What is the population in 6 hours?
8.
Wait.
813,773.
Something.
What?
So why is this such a large
E,
number?
it's above
Because
5.
what are we talking about? Bacteria, right? Yes?
If there's a decimal, would you round down or up?
I see. Well, with this one, you would round down because you're looking for the total number of life forms, and you can't count half.
I got 3.9.
3.9 is too low.
Okay.
Oh, times 10 to the... That's what you got too?
No,
What
it's-
could be different?
They did E. I think they did E to the 12 times. No, they did. Because I got 39 or whatever they're getting, and then I did. You do E to the exponent first, and then multiply that by 5.
Okay, so, and that kind of makes sense here because syntax is going to be different for different calculators too, so I'm not sure that iPhone syntax is the same. What calculator are you using, Gene? Oh. Serena, you got it right? Alright, I'm going to let you work with it, but anytime you have a specific number E, I want you to do E raised to the 12th first, then multiply by 5. Because that seems like the syntax for those phones. Alright, next we have this last one here, and this one's a true story. In 1966, 3 giant African land snails came to Miami. They came in a little paper boat. Yep.
How giant? Like, how big are
They're like up. I saw a picture.
Oh really?
It's giant.
They are big? Like,
Well, not that.
geese.
I don't know.
This
If
big?
actually-
Max
Can I
is
trust
like
you
a
guys
foot.
with these snail attacks?
Oh,
I think you can run away from it.
I
Can
really
I
want
try
one.
one?
Yes, please do.
It breathes fire also.
They're
Breathes
illegal,
fire.
but I want
Slimy.
I said they're illegal, but I want one.
Oh, well, there should be some left over. Let's see.
Maybe.
All right.
Oh my god.
So 3 giant land snails came to Miami. In 7 years, there were 18,000 snails. Assume
Wow.
exponential growth, obviously. Write an equation to model the growth. So, what is...
They're about 8 inches.
We're going to use this. Let's go through one at a time. My ending population is what?
18,000.
18,000. What was my starting population?
3.
3.
E. Let's see. So in this case, we have 7 years, but we have a growth rate that we're trying to find. Write the equation to model the growth. Okay. All right. 7. 7. Okay. So how shall we approach this problem? We want to solve for R. What do you think, Gene?
3, my bad.
Three.
Alright, 3.
Let's divide by 3 to start. Divide by 3 on both sides. You end up with
6,000.
6,000 is equal to e raised to the 7r. And then
Choose the root of E.
take the what of e?
ln.
The
Yeah,
I have log.
natural. So we're going to take the natural log here, the natural log there. The natural log of 6,000 you could find, that's a value.
8.699.
8.699 is equal to 7r. You see how we're going to solve this from here? You always use the natural log or one of your inverse functions of logs that was boxed here in order to eliminate your logs. The log function explains how this is all set up, as does the letter E, but when we get to this point, we're wanting to get rid of those values if we can. Last step, divide by 7. So it looks like our rate is going to be about, what, 1 point, wait, this is 8.6, 1 point, 243. All right, I keep the rate to, we'll keep the rate to the 1,000th place because for a large population, it's going to make a difference. You could even bring it further or keep the exact value in your calculator to work it. But now we know the rate. So
How many are there now?
What's that?
How many are there now?
We can figure that out. That's 1966. How long did it take for the population to double? So
2 days.
that was bacteria. Or that was like in a minute it'll double. Okay, so what are we going to? How are we going to set this up? We know our starting population was 3. We know the rate now. We know we're going to be looking for the time. What would the ending population be for part B here?
6.
6. It's going to double from 3 to 6.
Yes.
6 is equal to 3e
1.2.
1.243 t. Guess what? Same process. We're just looking for the amount of time instead of the rate. So go ahead and think about it. What's the first step? Check with your neighbor on the first step so you know the order of operation. It's similar here. Just like PEMDAS, what are we going to do first? Work your way from the outside in. Andrea, what are we doing?
divide by 3 on both sides.
3? 3. 2 is equal to e raised to the 1.243t. Okay. Gene.
So I figured out how much there are today. It's been 53 years since 1956.
Yeah.
2019. There are 1.224 more decimals times 10 to the 29.
29.
Is that accurate?
No, I feel like the population
Can we
would
assume that there's
plateau.
that many snails only in Miami?
They've eradicated. Vector controls come in with a bit of salt.
Just littered salt packets everywhere.
They have to do that in some places. Snails can eat all your food, all your leafy vegetables.
Oh.
Yeah.
They're the size of a human fist.
Really?
Yeah.
That's huge.
No way.
It's wild.
Like this way?
All right, so we know that there's I'm not sure the number for 29 zeros. There's a lot of these slugs if snails if they
In
were
Miami.
eradicated. They just start building houses out of snail shells. Like,
I have like watched a video of a lady that like owns them, and she just like has some in her house.
wow.
So they're pretty cool.
Climbing all over. They would be pretty cool to
She
see
has
it.
like a tank for them,
Oh.
but
Just around the house. I mean,
I just imagine like her yard. She's the one person that's like, no salt in my yard. Vector control's like, we
once
have to
when I
do
was
it.
little, I brought my mom's friend a snail, and she threw it on the ground and stepped on it, and I cried.
Yeah, it sucks.
oh, God.
Things that are gross, people say are bad. Things that can hurt you are
Snails are
bad.
gross. Did you know that?
Wait,
snails-
I'm sorry. No, it's good. I want to talk about snails, and I want to finish the problem at the same time, but I got to prioritize. All right, so we need to rid ourselves of the e. If you take the natural log of e, then we are right to, well, we have to take the natural log of 2, which you could find in your calculator, is equal to 1.243t. And if we just divide by 1.243 both sides, 1.243, then we end up with our t value. So it would just be the natural log of 2, divided by 1.243, which is something we have to find an actual value. Somebody do that on the calculator. What do you get, Jack?
0.5575.
0.5575.
75.
So since we were looking in years,
Half a year to double once and then.
yeah, 0.55, so half a year and change, so 6 months.
203 days.
How many?
203 days.
Oh wow.
What day is
6 months. Do 0.57 times 30. 31.
So it's like 6.5 months.
Okay, so we'll say 15 days. That seems long. I guess there's dang it, another snail joke. I guess there's snails. They're so slow. That's hilarious. I had to. There's a snail joke about something slow. Don't hate on snail jokes. Just kidding. I see that I'm having a conversation with myself now, so I'm gonna go. No. I actually like when that happens. All right, goodbye. That was weird.